So now I'd like to introduce today's speaker. Today's featured speaker is Olav Solgaard. Olav Solgaard is a professor of electrical engineering at Stanford University and the director of the Edward L. Ginston Laboratory. He earned his PhD degree from Stanford University in 1992, where his doctoral dissertation was the basis for the establishment of a Silicon Valley firm, Silicon Light Machines, also known as SLM, co-founded by Dr. Solgaard in 1994. He was a postdoc at UC Berkeley, and in 1995 he joined the electrical engineering faculty of the University of California, Davis. His work at UC Davis led to the invention of the multi-wavelength fiber optical switch, which has been developed into commercial products by several companies. Professor Solgaard's research interests include optical MEMS, photonic crystals, atomic force microscopy, and solar energy conversion. He has authored more than 300 technical publications and holds 50 patents. He is a fellow of the Optical Society of America, the Royal Norwegian Society of Sciences and Letters, and the Norwegian Academy of Technological Sciences. He also serves as the academic director for the new Internet of Things graduate certificate offered through the Stanford Center for Professional Development, which we'll talk a little bit more about at the end of the hour. So now I'd like to turn the floor over to Olav.
Thank you very much, Stephanie, and thank you to all of you out there who have logged on to hear me talk about things that are very dear to my heart. I've been working with sensors for a long time, so smart sensors is something that I'm very excited about and have been for a long time. The Internet of Things is newer, but it also has changed how we look at sensors quite a bit, and that's part of what I'm going to be talking about today. Here's my outline. I'm going to talk a little bit about sensor fundamentals because that allows you to sort of understand a little bit better how you should design and operate sensors in the Internet of Things sort of environment. And I will make the argument, and I hope I make a strong argument, that MEMS sensors, meaning sensors that are made with silicon foundry technologies, and I'll talk a little bit about what they are the ones that really are going to enable the Internet and has been doing so up to now and will do even more of that in the future. And then I will, towards the end, once we have sort of understood what the MEMS sensor is and what it does, we'll talk a little bit about Internet of Things and how that is going to be enabled by MEMS sensors. And I'll talk a little bit about the opportunities that I see really inviting you to sort of think about what Internet of Things can be for you in terms of challenges and opportunities. So that's towards the end. But before I even sort of jump into the sensor part of it, I just wanted to say a few things about my perspective on Internet of Things. And Internet of Things is showing it here as a pink cloud. Has many components to it, obviously. The sensors are that I have the perspective of sensors, but many other people look at it from different perspectives. So you might be an expert on the Internet and how you use the Internet. Of course, that's really the backbone that ties everything together. Machine learning and signal processing and the far end is also going to be very important, and many of the opportunities and challenges are there. Circuits and embedded systems are the things that are sort of takes the sensors and connects them to the Internet. So if you think of it in this way, the sensors are the structures that allows us to interact with the real world, and then we take it all the way to the other end through the embedded systems, through the circuits, through the Internet, through the machine learning and signal processing into the digital world. So the sensors are the interface, if you like. And that's why I think they are the most important. But other people have different perspectives on that. But here's some of the reasons why I think sensors are so important. You use sensors every day. This is a very, very incomplete list. Sort of sensors that you use every day involves the sensors that are in your cell phone in particular. You have accelerometers in there. Those are the ones that allows your screen to rotate so the phone knows what orientation it is. Gyros do some of the same things, also complements your GPS signals, timing circuits, microphones, light sensors, cameras, all of these things, heartbeat sensors and proximity sensors. Well, heartbeat sensor is the one that sits in your Fitbit or sort of device like that people more and more are using these days. In your car, you have many, many dozens of sensors, and I'm sort of showing an incomplete list here. The next thing I wanted to do was to talk about how sensors work. And of course, if you look at this list, and it's just a partial list, you will say that's not a meaningful question because they obviously work in many different ways. And so I'll try to find some commonality so I can say a few things about how sensors should work and how they should scale. So let's take a look at some of the ones that are out there. So this is Stanford work. This is a company called SiTime. What they do is make clocks, essentially. So these are clocks that are buried in your silicon chip. And timing is, of course, super important when you do communication and so forth. So this is the type of stuff that sits behind everything you do. You use it all the time. You don't even know it. The really cool things about this particular clock, if you like, is it works exactly like your grandfather clock at home. It has an oscillator, and the frequency of that oscillation is what gives you the timing information. Only this is a much more advanced thing and much more stable thing and much better in terms of keeping time than your grandfather clock. What we have here is if you look at this piece that is sort of, you can see as a cross section here. That is a mass that is suspended on the spring and is being driven in a resonance frequency. I'll talk a little bit more about the resonance frequencies in a second, but that needs to be very, very well defined so that you can get a very good time signal. So this is a mass on the spring, essentially. Here's another example. This is a MEMS gyroscope. It has several things that I want to say about this. This is a very complex structure. The first I showed was from Stanford. This is from UC Berkeley. I don't want to be too Stanford-centric, although you might feel that I am when I go through these slides. This is from Berkeley. The part that's a sensor is the gyro. So this is something that senses rotation. So it's similar to the timing circuit that I just showed in the sense that it's essentially a mass suspended on a spring. And that's the center of it, but there's also a whole lot more going on here, obviously. Here's some of my work. This is an atomic force microscope. So this allows us to sense things down to the nanometer scale, maybe as little as 1 nanometer, more typically 10 nanometer resolution. I showed two different versions here. Both of them have this same thing. There is if you look, there is a spring, and there's a mass associated with that spring, and sort of at the end of the spring, that allows us to vibrate. If you look at the one on the left, it sort of has a vibrating type of structure that like a cantilever or a springboard. The one on the right is more like a trampoline or something like that. But in both cases, you have a spring and you have a mass suspended from it, and that's part of the important operational characteristics of these devices. Here's another one. This is not really a sensor, but it's the type of stuff that could go into a LiDAR, for instance. This is a scanner. You see there's a mirror right there. That mirror is rotating. Again, it's a rotating mass on a spring. This is the type of stuff that they will sit in future LiDAR systems when we're really trying to miniaturize those and make them more efficient. So LiDAR is the ranging systems and imaging systems you use in self-driving cars. Maybe the most famous example is the Texas Instruments projection technology. They call it digital light processing technology. What that is a little aluminum mirrors, and one of them in the center is ripped off here to show you the sort of substructure. That substructure is very interesting, but again, it's a spring that sort of, you can see those little white pieces. Those are springs that connect it to the mirror, and the mirror rotates on the spring. Underneath there's all kinds of other things. There is integrated electronics in this particular chip, and that's a theme that I will return to on occasion. So again, we have this mass on the spring. Here's some of my work going way back. This is a grating light valve. These are ribbons that move up and down to create diffraction patterns that we can use to modulate light, and you can also use them as sensors in different configurations. This is again, sort of these ribbons have a mass, they have a spring constant, there are masses on the spring. So I think I'm trying to make the argument now that many sensors can be shown or can be sort of described and modeled as a mass on the spring. So now I want to show you a little bit about how that actually works. This is to give you a little bit of a feel for how these type of sensors work, and also how they scale. That's going to be my main point. So here we see sort of, this is a very simple springboard that I put together here on the panel. It's actually a hacksaw blade. If I engage it like that, you can see that it vibrates at the frequency. That's the resonance frequency. The resonance frequency is the frequency where you have maximum energy storage in terms of mechanical energy in the system. Now it moves pretty fast here now. But it is already a sensor. If I think of this as a sensor, right now, of course, it's actually a accelerometer. It sits in an accelerating field, and it's bent a little bit. You can't really see very much bending there, and that's part of the problem. That you need to be able to measure how far it bends. If I wanted to use it as a magnetic sensor instead, which I could do, I could bring this magnet in here, and you can see that it starts to bend. You're using your eyes. See, there it snaps in, and now I actually have a better accelerometer than I had before. At least it's more sensitive. Now you can more easily see that it bends. So now, even with just eyeballing this, you can see that there is an accelerating field this way. That's why if it was bent that way, instead you know that I had turned it upside down. But take a look at this. When I now engage it, I think that if you remember back to when I did it before, it moves quite a bit faster than it does now. So there's some things that happen to the physics here when I make it more sensitive. I made it more sensitive to gravitational fields, to just as a scale, if you like. I made a more sensitive scale or a more sensitive accelerometer by doing this, but I also made it slower. So that's the point that I want to make. If you now switch back to my slides here, and then we can see that what I showed you is essentially the system that I showed here. As a figure, there is a spring. That's a spring constant K. There's a mass that's moving on it. What I didn't show, I didn't talk about, was there's some damping, but you can certainly see that the swinging didn't go on forever. So damped out. Maybe it didn't damp out fast enough. I'm looking at it over here. Now it's still vibrating, but the vibration goes down. So there's a damper. And then there is something that we didn't really have in our experiment. I asked you to just eyeball how much the thing moved, and that's some kind of measurement for how much the mass is actually displaced. So if I think of this as an accelerometer, if I model an accelerometer this way, then I have a proof mass m that is going to be displaced by acceleration. So I accelerate the whole system, I get a displacement of m that, according to that gives me a force m times a, and that has to equal the spring force. So I can calculate, once I measure this displacement, I can calculate the acceleration that the mass has been subject to by knowing the spring constants, measuring the displacement, and dividing by the mass. That's my measurement, and this is how accelerometers work. This is how they work in your phone. This is how they work in your car. This is the exact mechanism that is being used when an airbag deploys in your car. But we have to sort of add a little bit more than just the simple formula that tells us what acceleration is if we have a certain displacement. We also have to realize that there is a bandwidth associated with that. We showed you that once I made the displacement larger by putting more mass on my spring, I had a slower resonance frequency. That's essentially meaning that I can't measure signals that are fast anymore. I can only measure slow signals once I do that. So that's the trade-off. The trade-off is shown here. Well, I should say one thing first. What I asked you to do when we looked at the video was to just eyeball the displacement. In a MEM sensor, we don't do that. We use some kind of electrical characteristics to measure displacement. And in our accelerometer, we use a capacitive measurement. So now you see that I have the same system I had before, but I added a little bit. I added a little circuit here that just basically put voltage on this plate across these two plates. So there's a counter electrode down here. The mass has become an electrode, and I have an electric field here. I can now measure the distance between those two plates by looking at the capacitance in this circuit, the capacitance between them. That's a very, very good measurement. I can measure very, very accurately this way. I mean, much less. I can measure distances that are much smaller than the size of an atom with these type of techniques. And this is part of my sort of small is beautiful argument. I can really measure very small displacements very accurately with this technique. If I want to measure something that's large and moves a large way, for instance, your car putting up to a stop sign or a traffic light, I should say, and then that after a little while it changes. Then it's measuring the position of your car magnetically, because that's too large distance. But for small distances, very accurate measurements, we use electric field. So once we have that, we have this measurement of position delta C. Then you can calculate the acceleration, like I said. And I can rewrite that in terms of that formula that I showed you for the resonance frequency in this way. So here, this is really the central design equation for an accelerometer. And of course, like I said, it's not only the accelerometer, it's all these other sensors and actuators too. So let's say that we wanted to now measure the smallest possible acceleration in a given bandwidth. So you want to go up to a certain frequency. There are certain signals that are so fast we don't care, but we do care about certain signals up to a frequency f. We could try to make that happen by having a very low spring constant and a very large mass. Then I would get a strong signal. But I also would get a very low resonance frequency. If you take a look at that resonance frequency definition, it goes as the square root of the spring constant over the mass. So that attempt isn't very good. Making a good sensor by making a very sort of weak spring and a large mass, well, it sort of works, but it doesn't work for the frequencies that we're interested in. What we can try to do is to make a miniaturized accelerometer. So now we have a very small mass, but we also then compensate by making a very, very weak spring. It's only really the ratio of the two that is important. So small is okay. It's okay to have a small mass because you can also make a weak spring and still sort of maintain a good, small, measurable acceleration. So what it really comes down to is to measure this displacement delta C very accurately. I asked you to just eyeball it. That's not going to be good enough. Using capacitors, we can measure that very, very accurately, but the key there is to make them smalls. So we want small structures because they have excellent position sensitivity. And you can design them to have any resonance frequency you want because it's a ratio of two different quantities, the spring constants and the mass that matters. This leads us to my sort of main argument over these last few slides, that we want to use miniaturized sensors, and we want to make them as small as you can possibly make them, and that's where MEMS comes in. So MEMS stands for Micro Electromechanical Systems. As I said before, these are systems or sensors that are made using integrated circuit technology. This is something that started way back, and Stanford was very central to it. This is some figures from an article I read in 1983 when it was published in Scientific American, and there's James Angel and the other gentlemen on this paper were here at Stanford at the time, and they did some very, very cool things. They wrote about this gas chromatograph, which is this. I'm going to explain how that works. It's actually not an example of something that's a mass on a spring. It's a wafer scale integration. It basically measures the composition of gases, or gas mixtures. This one here in the lower right-hand corner is an accelerometer, and then of course here you can immediately recognize the spring right there and the masses on it. This is the spring with the mass on it. So this is exactly like what I just showed you. And then here's another one. This is a pressure sensor. If you're measuring just sort of static pressures, like in a if you're just trying to follow the weather or something, then maybe the resonance frequency isn't that important. But if you use something like this as a microphone, which people do now increasingly, and many of you have these kinds of microphones in your cell phones. Then again, you have your resonance frequency as a key parameter, and you have the same argument for making it as small as possible. This was an incredibly powerful article for me. This is why I did what I did later. 3 years after this came out, I was at Stanford myself. And I lived in Norway when I read it. So this was sort of life-altering for me. Another thing that came out a little bit later was an article by Kurt Peterson. And the particular figure that I pulled out of that article, he had the article was, or the publication was called Silicon as a Mechanical Material, and of course that goes to the heart of what I'm arguing too. Silicon is really it. That is the best possible material to make sensors out of. He showed, and I'm sort of reproducing that figure here, a piece of work that was done by a PhD student here at Stanford, Roylance was her name, and she made some of the first MEMS accelerometers. So these are basically the forefathers, if you like, of the accelerometers that you have in your cell phone and in your car right now, the structure that you see there. And you're going to, of course, recognize, if you look at the structure, that you have a spring and a proof mass, exactly the same thing as I've been talking about. When we make MEMS, we make microelectromechanical systems, we use many materials. Essentially, if you go through the periodic table of the elements, almost all of them has been used in some fashion, either for fabricating MEMS or being part of MEMS structures. But they're really the most important parts. I'm not going to go through the whole list. We have a whole large number of materials that we like to use and that we occasionally use. The silicon is the main sort of mainstay, the one we use always. And the reason for that is that it's stronger than steel, lighter than aluminum, and it's single crystalline. It can also be used in polycrystalline form. The single crystal in particular has some very, very good properties. And there's no other mechanical material out there that's anywhere like it. If you think about construction and so forth, you think about steel maybe. And steel can be single crystalline, copper can be single crystalline, but they never are when you are talking about constructions. Only silicon is single crystalline in mechanical systems, and that's what makes it so unique. Let's talk a little bit about silicon. It's in the group 4 in the periodic table of the elements, and therefore it has a diamond-like structure, same as carbon when it crystallizes. That means that there are some certain planes within silicon that are more robust than others. So if you expose it to a chemical etch, some planes just won't etch as well as others. That means that you can make structures like these. So I'm showing you some structures here. There you can make very well-defined structures that are essentially terminating on these 1-1-1 planes, these crystalline planes that are more robust than the other planes. And what that allows you to do is to machine very accurately in parallel, and that's the key point. You can machine in parallel. You know, if you think about a machine shop, you have a machine there, you take a piece of aluminum or a piece of steel and you machine it, you do it at one at a time. If you go back to that, digital light processing technology of Texas Instruments, they have 1 million little machines on a chip. You couldn't possibly make them one by one. So this idea of making them all in parallel, making them by chemistry as opposed to by machining by chemistry, if you like, that's very central, and here's sort of the start of that. And here are some of those typical sensors. So one of the things that was very popular for a long time was to use piezoresistive sensors to do the measurement of displacement. I showed capacitive before. This is again from that same paper that the pressure sensor in the lower right here is from that Scientific American article by Angel and his co-workers. So this is one example of how you make a pressure sensor that is actually not capacitive in this particular case, but use another transduction mechanism. One thing that made a huge impact on the Silicon Valley was using these things for ink jet nozzles. So this is the basis of the transformation that happened within HP Hewlett-Packard when they became sort of a printer company for a few years. This is the heart of an inkjet printer. Of course, that was something that maybe has come and gone, but it was very, very important for a long time. So this is about machining things out of silicon, out of that material that I think so highly of. Another way of making micromachines is to deposit layers on top of silicon and then shape them. And this is a sort of canonical example of that. This is a Combdrive that could be sitting in something like a timing circuit or an accelerometer, and in fact, that particular technology has been taken to extremes by a number of companies and also institutions around the United States. So Sandia in particular made a very, very sophisticated surface micromachining process that you can make almost anything in. And then of course surface micromachining is also the underlying technology for that digital light processing technology that I already talked about a little bit. Another aspect of fabrication that sort of leads up to modern day micromachining in MEMS is deep reactive ion etching. Some of the most seminal work in deep reactive ion etching for MEMS was also done here at Stanford. How it works is that when you're trying to etch into silicon, you tend to sort of get shapes that are not exactly ideal. So if you take a look at that cross-section in the upper left-hand corner, I started to etch into silicon. I get these sort of sloped or rounded sidewalls. And what I can do then, and what happens automatically in this process, deep reactive ion etch, is that I deposit a polymer, and then I etch the polymer at the bottom of that hole. I etch it with a directional etch so that the bottom is exposed, and I can repeat the process, and I get, instead of getting sort of a very large sort of rounded sidewall, I get a sidewall that consists of sort of these little scallops, and they can be very, very small. So I essentially, when I've done this, I keep repeating this deposit polymer, then etch, deposit polymer, then etch process. I get something like what I show here in the bottom right-hand corner, where I basically get straight sidewalls. This was a huge sort of step forward, because now we could shape things differently. Now we were no longer dependent on the crystalline orientation of our silicon. Now we could shape it more arbitrarily. And so you can do things like I'm showing here. This is a very much used type of wafer in MEMS. It's silicon on insulator. What it means is that we have taken a silicon wafer, deposited oxide on it, and then put a layer of silicon on top of that oxide again. So that's what I'm showing on the top here. And then we just take that deep DRIE and we shape that top layer into whatever we want. And then we remove the oxide from underneath from where we want, so that we have freestanding structures. So this is essentially the basis process for a large number of MEMS devices. And here's sort of just one example. This is close to 20 years old now, so it's not sort of the modern types necessarily. But there's a couple of points I want to make here. It's a very simple process. What the structure you see is made in one mask in an SOI wafer, and it has a very, very powerful functionality. It's actually a fiber optic switch, this particular example. The point I want to make is that it's way too large. I said that MEMS, one of the fundamental reasons to use MEMS, and particularly in the Internet of Things, is where you're going to have so many sensors, is that they're super small. So the question is, how do we take this type of technologies? I talked about the chemical machining, the surface micromachining, and the deep RIE. How do we combine those to make really small sensors? So that, I think, is where the futures are. Very, very small sensors. And here's one example. This is from my own work, where we've been able to put a large number of sort of functionalities together. This is an atomic force microscope that is so small that it sits on the facet of an optical fiber. Standard optical fiber is 125 microns, so that is sort of a little bit more than 1/10 of a millimeter in diameter. And we have put a fully functional atomic force microscope on top of it. So that is sort of a tour de force in fabrication, if you like. But it also shows that we now have the technologies to go smaller. One of the key technologies behind that particular development is shown here. That's hydrogen annealing. So if you start out with a piece of silicon and you put it at low pressure in a hydrogen ambient, and heat it up a little bit, you will actually get sort of a reconfirmation of the silicon. It will flow. It still stay in sort of a single crystalline form, but you can make all kinds of very, very interesting devices. What I'm showing here is on the left sort of a photonic crystal. On the right, I'm showing that how you can actually use this to make voids. I'm going to it in a little bit more careful detail later. One of the picture in the lower left-hand side, or no, sorry, in the lower right-hand side is one of my favorites, because you can actually see there in those voids that I've created, you can see the facets, the crystalline facets of the silicon, sort of showing that this is in fact sort of a crystalline material, and even these voids show that very clearly. So just to show you, this is what I think is the basis for a number of sort of very important MEMS sensors going forward, sort of a technology that allows you to make more or less arbitrary shapes of silicon, and I'm demonstrating that here. So we start here with sort of following it numerically from 1 and then up. With a piece of silicon, we deposit a masking layer, we pattern something into that now at level 3, and then we etch into the silicon. So only one mask so far, and in fact it's going to only be one mask. Then I do a little trick there in number 5. I cover everything conformally with a thin film. And then in 6, I've continued my trick. I now remove things from the bottom. That's just sort of an idea we got from the DRIE, right? I remove things from horizontal surfaces. The top surface doesn't matter because it's already covered by such a thick passivating layer. And then I go and I etch a little bit further down into silicon with a directional etch. And in number 8, I can sort of complete the thing with an isotropic etch that creates these little spheres for me, these spherical hollows. And then I continue. I just do the same thing again in 9. I etch directionally a little bit further down. I do the conformal coverage in 10. I do the removal from horizontal surfaces in 11. I continue the etch in 12. I do another, this time much longer, isotropic etch in 13. And then I remove all the passivation in 14, and I have that structure that you see there. And then sort of the magic happens, because going from 14 to 15, what I've done is that I've done the hydrogen anneal where I have reflowed the silicon. And that allows me to make these very, very complex structure. So maybe this is a cross-section and sort of a cartoonish thing, so I want to show you some SEMs of that same thing to really show you what it looks like in real life. So this is before, this is at level 14 in the fabrication process, where we now cut out so you can see what it really looks like. There is this hole down in the silicon. There's a spherical hole sort of partway down, and then there's a void that is continuous, that stretches from hole to hole further down again. The top you can see is just these cylindrical holes. Now then we do the magic, like I said. Now we do the hydrogen anneal, and then this is what happens. So you can now see that those spherical holes that I had in the upper layer has turned into voids, and actually the silicon closed on top of them, and it closed underneath them, and it left two structures. It left these voids that are separate, and then it left a sort of continuous void underneath. Now I really have, this is actually a very good pressure sensor. We tested this in many different designs, because that set of small spherical voids on top becomes a photonic crystal that gives me high reflectivity. So we actually use an optical readout, an optical interferometric readout, to make this into a very, very precise pressure sensor. But the whole structure is made right there, and I think that you would agree with me that there's very few limitations on what I can make in terms of shapes with this. And the really, really nice thing about it is that these are single crystalline silicons, and they're extremely small, and those 2 points hangs together, because by making things out of crystalline silicon, I can make things very small and still have them be very, very robust. I can control the process better, so I can go to very thin films and so forth. So this is a very, very powerful MEMS technology. Here's I'm just showing a simplification of what I just showed you. This time I forgot, I forgo making that upper layer, and I just make a void. So you see that down there in 10, I just made a void. This is a pressure sensor by itself. The diaphragm is now sitting on top of a reference cavity. There's essentially very low pressure inside of the void that I created because we do the reflow, the hydrogen anneal at very low pressures. And then we end up with something that's a very simplified pressure sensor. And simplification is super important here, I believe. We really need to have things that are simple if you're going to go to the Internet of Things. So that's why I love this particular pressure sensor. It's just silicon, and it has just a void in it. And I can read it out capacitively, like we talked about before, how much that upper diaphragm has displaced, or I can measure it optically. There's a number of different things I can do with that, but it's super simple. So that brings me to sort of the point I wanted to make about smart sensors. So I've been working with, like I said, in 1983, I got super excited about MEMS, and I decided to come to Stanford to study that and work with these people. I never actually worked with Jim Angel, but I did play golf with him a few times. He's unfortunately passed away now. He was a great person. But I worked with people here who worked with MEMS. And one of the conundrums for MEMS is this idea that since we're making it on silicon, we should put some intelligence into the sensor. And I showed you examples of that already by the Texas Instruments. Texas Instruments technology. There's a set of switching transistors underneath the mirrors that I showed you. Analog Devices is the company that has really maybe gone the furthest in commercializing sort of capacitive accelerometers and gyros, and they also have integrated electronics on chip, and other examples of that. There are a few out there, but not many, because it's very, very difficult to do that. So when we are talking about the Internet of Things, where the sensors are going to be ubiquitous, so you might actually have to go with much cheaper elements than you can get with this process integration, where you do MEMS and CMOS together. I don't believe that is going to drive the Internet of Things. I think that what we really have to do is to do what I'm saying here at the bottom, to assemble things together, assemble the electronics together with very simple sensors to make the simplest possible devices and systems that we can make. So that sort of brings me back to the Internet of Things, and sort of like the proverbial elephant, the Internet of Things depends completely on your perspective or what part of the elephant you grab onto, right? I'm sort of very enamored with the sensors, as you have understood. I think they are the most important part, but that's of course my perspective. I think that's where the real world meets the digital world, and that's why it's the most important. Other people say, no, come on, the sensors have been around forever. What really is new here is the Internet and the machine learning, and then of course what's exciting is that what this can do for innovation and so forth. What we can do with big data, and then of course other people say, no, what really is the most important is how you implement all this with the circuits and the embedded systems and so forth. So exactly what the Internet of Things is and what's most important, I think that is sort of a question that I can't answer. My take is that the sensors are the most important. Those are the ones that enable things. But I do think I can say a little bit about opportunities and the cool applications. So let me have a stab at that. One thing that we hear a lot about these days, and everybody's excited about this, is autonomous vehicles, particularly cars, but it also extends to airplanes, drones, underwater exploration, and aerial mapping, and so forth. So here's sort of my little animation of that. So right now, the way most autonomous vehicles operate is that they have a LiDAR, that stands for light detection and ranging, and basically what I'm showing here is a laser beam sort of scanning across the field of view, registering things where things are. It's almost like a camera. There has a little bit more information because it can give you a little bit of motion information and so forth. And it also has maybe better resolution at the distance. But basically, you're getting an image of what's going on. That's not what our eyes do when we are driving. We do something quite different. We are aware of the environment. We don't photograph it sort of with a certain frame rate. We watch areas of interest. And we also are very good at picking up on motion, and that's what we need to do in sort of future self-driving cars. So here's sort of what I think it should do. It shouldn't be scan across. It should be, take a look. There, oh, there comes a dog running. I have to look at it. Right? That's what a human does. It doesn't look at the tree at all, because the trees, if they topple over, that's a problem if they move. But mostly, if they're standing still, they're going to continue to stand still. That's sort of at least the assumption. So awareness is really what the Internet of Things is all about. Being aware of the environment. One way to do that, to get that functionality I just showed you, is to use phased arrays. So this is one possible solution. We're working with that to have scanning mechanisms that allows you to jump to any sort of point in your field of view, not scan sort of like or get the whole picture at the same time. You're looking at exactly what is important, just like a human would. And that's where sort of some of the advantages are going to come when you actually have a self-driving car. I do think that there's a very good chance that it's going to operate a little bit more like a human in terms of what it actually senses and what it pays attention to. And that's what this particular technology allows you to do. So this is a MEMS phased array. I'm not going to talk too much about how it works, but it's essentially the same kind of structure again, right? Mass on the spring. Here's some other things that I think are super exciting, but also very troubling in some sense. We have wearable sensors. That's not really a big deal. Everybody's wearing a Fitbit or something like that these days. Then you can ingest sort of diagnostic devices in pills and so forth. That's a little bit more invasive. And of course, I'm working in the horrible end of this with implantable sensors. So I did what I'm showing here in the upper right-hand corner is an implantable microscope that allows you to follow cancer progression in animal models. So this is sort of very invasive, but it can also give you a lot of new information. And then the one on the bottom right is our sort of implantable microphone, I should say, that basically look at sort of acoustic fields in the body and how those, what they tell us about different diseases and so forth. So these are very, very exciting fields that are really, and one of the people who really go into this at Stanford is a young professor, Ada Poon, who's actually put together some of this slide, and she is in the process of revolutionizing this and making improving all aspects of it, and you will see more and more of this, and particularly sort of the ingestible, implantable sensors is just starting out. Now, this is what they are, and I think that we can see more, we expect to see more of them, but what are some of the challenges and opportunities that represents? You're going to get just more and more health records, all of us, and we need to integrate that so we can really sort of get at the important information. That's a big data problem and maybe a machine learning problem. Data security, of course, is super important. We don't want people to hack our information. But here's another thing that I'm talking about here, false positives. So if you have a sensor that tells you that you might have a symptom that is problematic, then you go to your doctor. So the doctor's office is going to be full of healthy people but that are anxious about some device that they have that tell them something. Now, that, of course, if you ask doctors, they will say that's going to be a huge problem. It's going to be a nightmare. This is not going to work. But you can't turn that around because there is an energy there. People care about their own health. What we really need to get to is that you don't really just go and bother the doctors about false positives. What we do is that we become an assistant to the doctor, so somebody who can actually work with the doctor on the team. And I think that the Internet of Things and sort of those medical sensors are going to help us do that. Now, so in terms of opportunities, if you can find a business model that allows you to tap into that energy that people have about caring about their own health, I think you will win big. I don't know how to do that. This has so many aspects to it. Sensors are only one of them. So to end up then, so what do I see as the big opportunities of the Internet of Things, and what are the cool applications? I think that the Internet of Things, like I said, even if I can't really define it, it's about awareness. That's really one way to if you want to use one word that describes the usefulness of the Internet of Things, it's awareness. That's going to lead to efficiency, safety, sustainability in transportation, healthcare, food, in production, transportation, storage, preparation. You're going to get smart cities, smart homes, and so we're going to have a lot more awareness of what's going on around us. And if you talk about it from a company point of view, if you want to, or a sort of entrepreneurship kind of point of view, there's going to be a lot of people trying to develop business concepts around this. So you really have to be unique. You have to have your own secret sauce. I think unique sensors is easy for me to think about. How you make the sensors unique. It's not that you can measure things that haven't been measured before, but you're going to use them in different ways, and you can integrate them in different ways. You're going to communicate with them in different ways. That's the uniqueness that you need to develop. You can also be unique on how you execute. That's a lot harder, at least from my point of view. But of course, people are going to win there too. Part of the execution is how you actually do some of these things with the circuits and the better systems. Better user interface, I think, is super important. We really need to solve the big data problem by having machines take that over and present us with information as opposed to data. But maybe the most exciting things about the Internet are things that it can affect us in so many positive ways. If you work on this, you have sort of so many opportunities to do good. Now, if you also do well, that's okay. But I think that doing good is really, really what makes me excited about the Internet of Things. So with that, I want to thank you for listening, and I hope that you have some questions. And we're going to take those now, I believe. Yeah, so I'll start by the question about limitations on miniaturization. So the question is there any limitation for miniaturization of MEMS sensors as the structure reaches the nanoscale? And clearly there is such limitation. There are such limits. Once you are getting down towards the sizes that are comparable to sort of atomic distances or separation in silicon, this is a crystalline material with a very distinct or very well-defined atomic distance between the nearest neighbors. Once you start to approach that, of course, everything that I talked about becomes very different. So I think that we can sort of take many of the concepts that we have made and scale them down into the hundreds of nanometers, certainly, and maybe tens of nanometers. But once we smaller than that, and of course that's where electronics already is, right? So the manufacturing base for going to those kinds of sizes are there. We can go there with the technology that's been developed for electronics. I have a hard time seeing sensors that where the overall sensor is less than 10 nanometers. That would be crazy, it sounds to me. So maybe somewhere in the tens of nanometers where the limits are, where we have to sort of start doing things very differently. Yes, so I think that's sort of my answer to that question. So the next question goes to this thing about integration. Is it possible to etch MEMS sensors on the same silicon die as an integrated circuit? And that is possible, and there are many strong examples of that, and I keep bringing up this digital light processing technology of Texas Instruments. I think that's a tour de force in technology development. It has electronics sort of underneath, and it has built MEMS on top. So that's definitely one example of that. And there are several other companies that's done the same thing. I think that to do that, if you look at the Texas Instruments technology, it's only rarely updated because it's so difficult to do an update of a technology like that. It took a long time to develop. I'm not going to try to hazard a guess as to the total development budget, but it was going to be in the hundreds of millions. And that means that only a few applications can really have the ambition to do something as complex as that. So I think that for most Internet of Things sensors, you will not do that, just simply because there are other ways that are more cost-effective with the type of diversity that we expect to see in the Internet of Things. And then there's a couple of questions about reliability. And let me just read a couple of the questions, or at least one of the questions. Is there any mechanical wear out with time for MEM sensors? And of course, the answer is, on the face of it, the answer is yes, but I'll say some more things. The next question along the same lines is that the MEMS currently undergo extensive testing during manufacture. What is the current thinking on long-term testing on MEMS that are in current operation? Question goes to the reliability factor. So I'm just talking about the reliability in general first. There is a large number of MEMS sensors out there. Actually, we expect to reach 1 trillion sensors. A very small fraction of them, maybe 1 in 1,000 or 1 in 100, is going to be in the Internet of Things. There are many systems that aren't going to be connected like that. And they are shown, though these sensors, and we're talking about billions of them now, have shown excellent reliability. And it isn't strange, because the smaller things are, the more robust they are. And of course, then you also add that this is the best material known to man in terms of purity, and it's pure. It's a clean crystal. It's a monolithic crystal in many cases. Long-term stability is excellent for all MEMS devices. Let me just take one sort of example that is somewhat facetious. But if you take a BMW, which many people will say is an okay car, right, and you shake it, you'll find that the first resonance frequency is somewhere in the tens of hertz. That means that it's really not that good. If you take a MEMS device and shake it and you try to look for the first resonance frequency, it might be in the millions of hertz, in the megahertz, or at least in the hundreds of kilohertz. Basically what I'm saying is that any MEMS device or any good, well-defined designed MEMS device is something on the order of 10,000 to 100,000 times more reliable than a BMW. Now, I am being facetious here, but it does go to this reliability. Now, there were some more specific questions in there that had to do with how it tests, and that is difficult. I think that it's clear that the Internet of Things is such an explosive growth that we are going to not test enough. For some of these applications, we might have to do more testing. As a general rule, I think that MEMS is very reliable, but of course you have to test for it. The next question has to do with something I didn't touch on at all, and that is about how do you power these sensors. So the question is about energy harvesting methods. Are there any MEMS sensors that can be self-powered by harvesting ambient energy? And again, this is a big field. I didn't talk about it. It's very, very important. If you're going to have sensors everywhere, having batteries is of course possible. Some of these sensors are using very little energy, and you can wake them up only occasionally when you need to read their data, and that could get you into very, very small sort of power, for average powers, so you might be able to, on even very small batteries, operate for 10 years. But of course, what's alluded to here of energy harvesting is also very, very interesting. So the most obvious is to use solar cells and things of that nature if you're operating in an environment where that makes sense. Even an indoor environment has a lot of light energy typically, so you can combine that with sort of a rechargeable battery. You can have something that essentially lasts forever. I should put that in quotes because nothing lasts forever, but at least you don't have sort of a power lifetime that's obvious. There's also a number of developments that goes to things like extracting energy from vibration and so forth. You can think of it if you have a pressure sensor in a car tire, and that's more and more common these days, so that you know whether you actually have a problem with your tires. You don't really want to have a battery in there, but there's also there's a high energy environment because of all the rotation. So you should be able to, you might have a battery, but it's a rechargeable battery that recharges through that energy that you can extract from the rotation that's going on. So energy harvesting methods is super important. And when you're saying that the MEMS sensors are self-powering, that's a slightly different question, though, because now you're talking about the sensor itself being the energy harvester too. And my general feeling there is that it's better to separate those two functions into two different devices and put them together into a well-functioning system.
So we're at the top of the hour, so to be thoughtful of everyone's time, why don't you take 2 more questions, Olav?
Okay, yeah, so let's see, the next one I haven't read yet, so let's see, I'll read it out loud now. How do you see IoT devices catching brain waves, cell metabolism, and help with deep learning, disease prevention, and other body cures? That's actually more than one question, I think, but let me try to take a stab at that. There is definitely, and I did mention Ada Punas, one of the sort of premier researchers in this field, lots of people who are interested in neurology, and they're using both sort of optogenetics and also a number of different kinds of probes. Some of them are based on MEMS technology. So the brainwaves is sort of a little bit of a nebulous term for me, but neurology and sort of action potentials and things of that nature are being measured with sensors, and they will be part of the Internet of Things at some point, although now we're talking about something that's very, very invasive, so exactly when that kind of data will be part of the Internet of Things is not obvious to me. Cell metabolism and so forth, that is something that is much more straightforward, and we have quite a few sensors that are sort of in a microfluidic systems where we do all kinds of things like drug discovery and so forth, and there's a large number of MEMS sensors there. Deep learning, of course, I think this is sort of disconnected from the first part of the question. Deep learning is a super important part of the Internet of Things. I mentioned machine learning. Deep learning is a variation on that. I'm not going to go into the details of the differences, but the deep learning is absolutely essential for dealing with the big data that we're going to get from all these sensors. And the last part of the question, how does this play into disease prevention and other body cures? Having more data must help, but it's not obvious how you do that. So this is really one of the key questions, and maybe one of the key challenges, or if we could turn it around, key opportunities of how do we actually use more data to make healthcare more efficient and hopefully also less expensive and also have better outcomes. It's not obvious that that's going to happen, and doctors are petrified of it. Yeah, so I'll take the last question. I'm concerned about people hacking into self-driving cars, another large object to cause harm. What are the safeguards? So this is, of course, very well-founded fear, because there has been examples already of cars being hacked into, and people, if they were malicious, I think most of the examples we heard about have people doing it for demonstration, where they could have done things like lock the wheel and stuff like that at speed. This is definitely dangerous territory. What the safeguards are, we have the same. This is actually something that needs to be studied very carefully. Now, if I take the self-driving car as an example, I think that you have to be aggressive in employing them, even if in spite of the fact that I really don't have a good answer to this question. And the reason for that is that, roughly speaking, 40,000 people die in traffic in the United States every year. If we can reduce that number substantially, even if we are opening ourselves up for malicious hacking, if the total outcome is that we reduce that number substantially, then we have to go for it. That's why I think we have to be aggressive. But this question, of course, points to some of the most frightening things around the whole Internet of Things, and I don't know what the safeguards are, other than being very vigilant and making the systems as hack-proof as possible. And if we are to believe certain news outlets, we don't even have a hack-proof electoral system in this country, right? So it's a very tough question, and I don't really know the answer. In some cases, we have to go forward without being 100% secure. In other cases, the downside is so huge that we just basically cannot take the risk. So that's maybe one way to answer the question is that we basically have to parse the risk-reward and go forward where it makes sense.
Great. Thank you, Olav, so much for a wonderful presentation, for taking time to answer all these attendee questions. And there were many we even couldn't get to, which shows me how much interest there is in this field. A reminder to all of the attendees, recording will be made available within a week and sent out to those who registered. And we just want to thank you. Thank you so much for taking the time to attend today, and we'll see you at our next webinar and hopefully in our Internet of Things graduate certificate as well. Thanks so much.